Good morning. Today is January 21st, and due to the winter weather conditions, we moved remote today, so I'll just be recording a lecture for you to view from home today. Unfortunately, just cold and no snow so far, so I can probably get rid of these goggles. We're just going to pick up right where we left off, so we're going to continue with limits. We're going to learn about continuity and average rate of change today. I have a document camera here at home, so I'm just going to switch over to that now. All right, so if you would like to follow along either on scratch paper or your printed out prepared notes, we're going to work in section 1.2, so limits and continuity. Before we start working these examples, I just want to talk about how last time we assessed and evaluated limits using graphical methods. So kind of the idea was we look at a left-hand limit, we look at a right-hand limit, so that's talking about in terms of the number line. So to see if a two-sided limit exists, both the left-handed and the right-handed limit had to exist and had to equal the same value. So here we're going to evaluate using a method called direct substitution. So here we're not going to deal with graphs in the beginning of the lecture. We're just going to use a technique that is very straightforward. So here in example 1a, we have the limit as x approaches 4 of x squared minus 3x plus 7. And so evaluating this, really all that we have to do, so we want to write the limit as x approaches 4, x squared minus 3x plus 7. So here for the direct substitution, we do exactly what it sounds like we do. So we directly substitute in x equals 4. So here, 4 squared minus 3 times 4 plus 7. So 4 squared, of course, is 16. 3 times 4 is 12. We add 7 to that. So 16, take away 12 is 4. We add 7. We're left with a positive 11. And so here, we don't have to have a graph in order to assess a limit. Using this method, the direct substitution, it's very nice. It's very nice when it works. It doesn't always work, and we'll learn a separate technique momentarily here. But the preferred method here is just start off by trying to plug in that value. So the limit as x approaches 4, we can just directly plug in 4 everywhere that we see in x, and then see if we get some value. I want to take a moment here to talk about notation. Okay, so of course, in math, notation really matters. A lot of mathematicians, myself included, are pretty picky about notation. So here we write this limit notation. So we learned this last class. So the limit as x approaches 4, okay, of that function. So here we wrote the function out. We didn't just write f of x. That part doesn't matter so much. If you define the function ahead of time as f of x and you want to write limit as x approaches 4 of f of x, that's totally fine. But the big point is that this piece should remain with our function until we get to the point of the direct substitution. So notice here, the limit as x approaches 4, that's like a piece of the instruction. So what are we doing to this function? We're taking a limit as x approaches 4. The next line here, I just went ahead and used the direct substitution method. So I plugged in 4 for x. Notice on the second line, this limit notation goes away. Okay, I've already applied the instructions here. Okay, so I've substituted in a 4 for x. So the notation here stays with the first line. Once we evaluate the limit, so once we plug in x equals 4, we no longer need to write the limit as x approaches 4. So hopefully that's clear. A very common mistake I see when teaching this class is that maybe after using the substitution, students may erroneously copy down this limit as x approaches 4 onto the next line, or sometimes even the final answer, they'll say limit as x approaches 4 of 11. Really, this is our final answer. It's just a number, okay? So as x approaches 4, it looks like the y values approach 11. All right, moving on to the next. Here we have the limit as x approaches 2 of x to the 4th minus 5x cubed plus x squared minus 7. Okay, so again, we're just going to move with the direct substitution method. So I'll label this as A. Here we have B. So the limit as x approaches 2 of x to the 4th minus 5x cubed plus x squared minus 7. So direct substitution, next line, I'm going to replace every x with a 2. So here we have 2 to the 4th minus 5 times 2 to the 3rd plus 2 squared minus 7. Right, and so now just kind of knock out term by term. So 2 to the 4th, that gives us 16 minus 5 times 2 to the 3rd. I'm going to do that in one swing here. So 2 to the 3rd is 8. 5 times 8 would give us 40, so minus 40 for this piece. Plus 2 squared, of course, that one is just 4. And then subtract 7. Add and subtract everything across, we get a negative 27. So, direct substitution method is quite nice. Really, it should be your first method when trying to evaluate these limits with a function. There are cases where, we run into a wall and we have to apply maybe a more advanced technique. We'll continue with that in a moment. So let's do a few more of these. And I encourage you guys watching at home, if you understand the concept or think that you do, a great way to practice is to pause the video, maybe work ahead, and see if you get the same answer that I get. So I'll just continue with C. We have the limit as x approaches 0 of the square root of x cubed minus 3x plus 2. Okay, so this one looks a little bit trickier because now we have the square root component. But really, same method applies, so let's just go ahead and attempt our direct substitution. So the limit as x approaches 0 of the square root of x cubed minus 3x plus 2. Let's just go ahead and substitute in a 0. So we get 0 cubed minus 3 times 0 plus 2. And here we just end up with the square root of 2. So of course 0 cubed minus 3 times 0 is just 0. Add 2 to that, we get a 2. Here let's leave it as an exact answer, just square root of 2. Alright, moving on to D. So we have the limit as x approaches 3, x squared minus 8 all over x minus 2. So here, just going to do it on the same line. Just a nice direct substitution. So we're going to plug in 3 up top, so 3 squared minus 8, and on the bottom, a 3 minus 2. And there we have it, just a 3 squared would give us a 9. 9 minus 8 gives us a 1 on the top. 3 minus 2 on the bottom is of course a 1. So for D, we just get a limit of 1. So the limit as x approaches 3 of x squared minus 8 over x minus 2 is just equal to 1. So really nothing to it so far. We're doing calculus. It feels like we're doing algebra because really with this method that's all that we're doing. So direct substitution is nice. Just going to keep working. So limit as x approaches 5. So limit as x approaches 5 of the square root of x squared minus 16. Another square root problem. We're not going to let it stop us. Here we just plug in a 5, so we get the square root of 5 squared minus 16. So 5 squared, of course, is 25. Take away 16, so we get the square root of 9, which is just 3. Right, let's do another one. So for F, limit as x approaches 2. Here we have the square root of x squared minus 9. So we're going to do the direct substitution. We get the square root of 2 squared minus 9, which is of course square root of 4 minus 9, which here we get the square root of negative 5. And this is our first big issue that we run into. So here in the realm of real numbers, there is no square root of -5. I know maybe in algebra pre-calc you talked about the imaginary numbers, but here with these limits, we are talking about the realm of real numbers. So for this particular limit, we get that limit does not exist. So the limit as x approaches 2 of this function, that does not exist. So 2 is actually not a part of the domain of that function. Moving on, so this one, part G, this tricks a lot of people. This one's just a little fun for me, I'd say. So what kind of function is just y equals 7? So here we're taking the limit as x approaches 2 of just 7. Okay, so a lot of students get very confused when they see this, maybe on a test, on a quiz, or just for the first time. So they say, well, there's no x involved. What do I do with the 2? Let's just take a moment to think about what does that graph of just y equals 7 look like. So just a quick little sketch. Here's our y-axis, here's our x-axis. Y equals 7 is just a horizontal line. Okay, it's just a horizontal line at 7. Okay, so the slope of 0, we learned or were refreshed that a slope of 0 just indicates a horizontal line. And so here the limit as x approaches 2 of just 7, kind of think about your way with this graph. No matter where we are on the x-axis, so any point for x is going to have the same coordinate of y of just a 7. So here, here's x equals 2, here's y equals 7. So for this one, the limit as x approaches 2 of 7 is just 7. And really, you could throw in any value of x, so the limit as x approaches 0 of 7 is still just 7. The limit as x approaches 1 million of 7 is still just 7. The limit as x approaches -2 would still be 7. So this is just a constant function. No matter what point that we look at, it's still going to have that y value of 7. So when you see something like this, rejoice. I promise it's really not tricky. You don't have to do anything with the x at all. This is just always a limit of a constant function. It's just going to be whatever that constant is. All right, let's do the last one of these before we learn the new technique. So for h, we have the limit as x approaches 2 of x minus 2 over x squared plus 4. All right, and so still we're just going to use the direct substitution method. I'm going to slide up my Mean Girls pink scratch paper here. So direct substitution, we're just going to swap in a 2 for the x. So 2 minus 2 on the top, 2 squared plus 4 on the bottom. So up top, 2 minus 2 is 0. On the bottom, 2 squared plus 4. 4 plus 4 would just give us 8. Don't get lost here. A 0 on the top is totally fine, right? So this just gives us a value of 0. Okay, so the limit as x approaches 2 of x minus 2 over x squared plus 4 is just 0. Okay, so totally valid to have a 0 in the numerator. So on the top of the fraction, having a 0 is totally okay, so long as there isn't a 0 in the denominator or the bottom of the fraction, right? That is when we run into issues. Okay, so that gave us a hard time in algebra. It's going to give us a little bit of a hard time again here in calculus. So that will be a nice segue into our next topic. So we will focus on a new method, so finding limits of indeterminate form. So I just want to reiterate, if you evaluate a limit using direct substitution and you get a 0 on top of the fraction, that is a-okay. We don't have to do anything different. It's just when we get to this new form. So let's focus on one of these problems. So I'm going to look at example 2. This says, find limits of indeterminate form 0 over 0. Try factoring. Okay, so that's exactly what we're going to do. We're going to factor here. So looking at this first problem, we have the limit as x approaches -3 of x squared minus x minus 12 all over x plus 3. Okay, and so for these, still, let's try our first method of attack, which to me is just the easiest, the most straightforward method, the direct substitution method that we just did those 8 example problems up. So we'll start by applying a direct substitution. So plug in -3 every time that you see an x. So up top we get a -3 squared minus a -3 minus a 12. And on the bottom, -3 plus a 3. All right, you could probably guess because of the instructions here, but up top we get -3 squared is 9, minus -3 gives us 12, and then subtract 12 is a 0 on the top. We have a -3 plus a 3 on the bottom. That gives us a 0 over 0, okay? But don't be so fast to write a big D and E on your paper. Not yet, at least. We could try something else. So here, let's try again. We're going to try and use factoring. Okay, so we're going to factor this top. Let's look at the limit as x approaches -3. Up top here, we want to think of two numbers that multiply to be -12, but add up to be -1. Think x plus 3, x minus 4. Seems like a good choice here. X plus 3. If you're still a little rusty on factoring at this step, it really doesn't hurt to FOIL the two factors that you got to make sure you arrive to the same polynomial on top. And what's nice here is that we have a factor of an x plus 3 up top and x plus 3 on the bottom. So actually these will cancel off. And so this is the same as the limit as x approaches -3 of x minus 4. And really over 1, I didn't write the divided by 1, but since these canceled off, just leave it like that. And now there's really nothing stopping us from doing the direct substitution at this step, right? So we can go ahead and take the x approaches -3. Let's swap in. So x becomes a -3. Take away 4, we get a -7. Right, so here, factoring really saved us, and that is our final answer. So we would say the limit as x approaches -3 of that function is -7. So last time we talked about piecewise functions. We looked at the graph of piecewise functions. We also looked at graphs that had asymptotes and holes. You may think back to college algebra or whenever you first learned about holes and asymptotes. So what is the main difference? So an asymptote occurs when you run into that divide by 0 issue, but you don't have anything that will cancel off with it. So notice in this problem, we have that x plus 3 factor on the top and the bottom. That goes and cancels away. So still, if we were talking about this function and trying to graph it, we wouldn't be able to plug in an x equals -3. We would still run into that divide by 0 error. So actually for this, -3 is not a member of the domain of this function. We would have a hole in the graph, but we can use limits to kind of assess where that hole might be. Okay, so there's not an asymptote here, there is a hole. So factoring is your friend. Try the direct substitution method first. If that doesn't work, then maybe try factoring. Once you factor, then apply the direct substitution method. So let's do another one of these. So this is example B. This was example A of section 2 of 1.2. So here we have the limit as x approaches 2 of 3x squared plus x minus 14 all over x squared minus 4. All right, and right off the bat, I would say this one looks like it's going to be a little bit harder to factor. We have kind of a nice technique or nice property of these that you can kind of use to think your way through. But let's start by just doing the direct substitution method. Because it's under this section, I promise you it will turn out to be 0 over 0, but still it is good form. So let's just try to swap in not a 0, excuse me. So 3 times 2 squared plus 2 minus 14 up top, all over 2 squared minus 4 on the bottom. Sure enough, 12 plus 2 is 14. Take away 14, we get a 0 up top. 2 squared minus 4 is 0 on the bottom. So we're going to try again. And this time, we're going to factor. So here we have the limit as x approaches 2. Start with the denominator because it's much easier. So of course, this is a difference of squares. We're going to end up with an x minus 2 and an x plus 2. And now for the top, how can we factor this? So we're going to need something that's got a leading coefficient of a 3. So to get that 3x squared piece, I know I'm going to deal with a 3x times an x. But now what, this to me is so cool. So, and it really works because, if you see this on a test, on a quiz, on a homework, and you have to do this indeterminate form, in order for us to be able to plug in a 2, really we need to get rid of this factor, okay? This x minus 2 on the bottom, that's what's throwing us off here, okay? So that's what happens if we plug in this 2. This piece is what is producing that 0 in the denominator. And so in order to get rid of this x minus 2, we would need an x minus 2 up here. So if you're a little rusty at factoring or maybe just need a push in the right direction, start with that. Think about what needs to go away for this problem to work out. And for this, I need to get rid of this x minus 2 in order to evaluate this limit. So I'm going to start and just think, okay, maybe there is an x minus 2 factor up top. Now, it doesn't always work this way. Of course, in these examples that we do in class and often on the homework, they are doctored and cooked up examples so that we can demonstrate this concept. So it often works in those. It doesn't always, but it's a good place to start. So I'm going to try and use a factor of x minus 2 here, and that can help me think about what goes right here. So in order to get this negative 14, we already took out the negative 2, so what goes here should be a 7. Let's just do a quick FOIL to make sure we arrive to what we expect. So 3x times x gives us the 3x squared. 3x times negative 2, that will give us a negative 6x, but then we add 7 times x to that. So negative 6x from the outer terms, positive 7x from the middle terms. That does give us the positive 1x in the middle here. And then finally 7 times negative 2 gives us the negative 14. So I think that's a cool way to get really a huge hint on how to factor these, right? Because they're not always so obvious or so easy. So limit as x approaches 2. Now we factored, we get a 3x plus 7 times x minus 2 on the top. We get an x minus 2 times an x plus 2 on the bottom. Of course, these will cancel, so the x minus 2 and the x minus 2. So now we're just left with the limit as x approaches 2 of 3x plus 7 over x plus 2. The limit notation stays with it as long as there are x's involved, right? So until we do the direct substitution, we write that limit as x approaches 2. So here I'm going to go ahead and evaluate, right? I can plug in x equals 2 to the top and the bottom. So here we get 3 times 2 plus a 7. We divide by 2 plus 2 on the bottom. So 3 times 2 plus 7, that will give us a 13, and on the bottom, a 4. And I'm just going to leave it like that. So improper fractions are fine here. So both of these, we had what's called the indeterminate form. That just means when we get a 0 over 0, we're not really sure what's going on with that limit, okay? So if you ever arrive at this 0 over 0, your best bet is to factor. Hopefully something cancels off. If it does cancel, then you can reevaluate the limit using direct substitution. There are times with these where nothing cancels and we kind of run out of methods. And at that point, that is when you can say that the limit does not exist. So there are a couple other attempts that we can do for various forms of these indeterminates. Well, let's talk about the next big concept from this section. So we're going to talk about continuity. Okay, so before we talk about the formal definition of continuity, I think it's just helpful to look at some graphs. Okay, so a function is continuous conceptually if the graph is connected. So if you can draw it without lifting your pencil. Okay, so here we're looking at 3 different graphs. And as we stare at all 3 of these, I'll tell you guys, 2 of them are continuous and 1 is not. Okay, so just based off of this sketch of an idea, which one is not continuous? And if you said the bottom graph, then you would be correct. Okay, so notice here, this is like maybe a cubic function. It's got a slide shape. Okay, so if I wanted to draw this shape, I could do so without having to lift up my pencil. Just like here, this parabola shape, I could draw this, I could sketch this without lifting my pencil, right? So I could just do it in one motion. Whereas this appears to be a piecewise function. So if you wanted to draw this graph, you start over here, you sketch up until this point, you'd have to pick up your pencil, get to this point, and then continue. So really, that's all it is. Continuity, the big picture is just, can you draw the graph without lifting up your pencil? Is it connected? Okay, so that is like the main idea here. So for these 2, they are both continuous, so I'll label and draw arrows. This one is not, so I'll say it is discontinuous. Okay, and it is, in particular, it is discontinuous at x equals -2, okay? Right here, this is the location where kind of everything went wrong as far as continuity. So the top 2 are continuous, the bottom one is not continuous. So hopefully that makes sense. Let's talk about the more formal definition of continuity, okay? So here, we say that a function f is continuous. So a function f is continuous at x equals a if the following conditions are met. Okay, so if f of a is defined, so f of a is defined. What does that mean? So here, like, imagine we're checking, is this function continuous at some point? So maybe we're checking at x equals 2. Okay, so f of a has to be defined. So in other words, there has to be some output, some y value for that function at that point, x equals a. Okay. So in this, let's look at these 3. If we're checking at, say, x equals -2, so f of -2 in this graph, it looks like it goes a little bit off of the page, but maybe it would shoot up over here to like 10 or something. Better example maybe at f of 0. Is this continuous at 0, right? So here, when x is 0, y is 2. This one, when x is 0, y is 0. So f of a must be defined. The next is that the limit as x approaches a of that function exists. Okay? So the limit as x approaches that point that we're checking must exist. So finally, the limit of that function as x approaches a has to be the same as the defined point. Okay? So we'll talk more about that in a moment. All 3 of these conditions have to be met for a function to be continuous. So what's nice about when you're checking, is a function continuous? If it fails to meet a single condition, then you can just stop and right away say, oh, this is not a continuous function. So for example, if we're checking this, so using the more formal definition rather than just, oh, I can't draw it with my pencil, let's check, is this continuous at x equals -2? So step 1, is f of -2 defined? And in fact, in this function, it is. So we have a filled in circle. So when x is -2, y is -3. So it meets the first condition. So f of -2, in this case, is equal to -3. So it passes that. but 2, does the limit as x approaches -2 of that function exist? And in this case, no, right? So if we look at the limit as we approach -2, coming from the left, so the limit as x approaches -2 from the left, looks like we're arriving at this value of +2. But then if we check the right-handed limit, so the limit as x approaches -2 coming from the right side, we're approaching -3. So here we get that the limit does not exist, okay? So for this one, we can stop there. The second condition was not met. We don't have anything to go off of for the third condition, okay? So if any of those conditions fail, then it is automatically not continuous. So let's move on to the next page. Let's talk about limits and continuity with more visual examples. So here we're looking at example 3. Explore limits and continuity in the following examples. And so for you viewing at home, it hopefully is clear to see, but we actually have an open circle here. So when x is 2, y is +1. And then we have a filled in circle here that x is 2, y is 2. Okay, so open circle here, filled in circle here. I apologize, I know that's a little bit hard to see right here, but hopefully you're following along with the printed out notes. So first we want to check what is f of 2. Okay, so here f of 2, when x is 2, y is also 2, so we go off of the filled in circle, not the open circle there. Right, so really that's the first condition, right? That is the first condition for continuity. So does f of 2 exist? And really we're talking about the main picture here is it continuous at x equals 2? You can probably look at it and tell, but we'll talk about why it is or is not. Now these are really all step 2 in 1. So we want to see, does the limit exist? Okay, so we did a couple of these last time I saw you guys. So let's talk about first, the limit as x approaches 2 coming from the right side. So just as a reminder, the 2 with the little plus sign, superscript, that really means we're approaching +2 coming from the right. Okay, so starting over here, we trace with our pencil. As we get closer and closer to x equals 2, it looks like we're arriving at a height of y equals 2. So the right-sided limit is 1. Now we'll do the same for the left-sided limit. So remember 2 with the little minus in the superscript, that means 2 coming from the left. So +2 coming from the left does not mean a -2. So we start over here and we just get closer and closer and closer to x equals 2 coming from the left. We arrive at the height of 1. Okay, so the right-hand limit is 1, the left-handed limit is 1. Therefore, the two-sided limit exists since those two arrive at the same location. Okay, so the left-hand limit and the right-hand limit are the same. So it tells us the two-sided limit is 1. Okay, so far for the test for continuity, this graph, this function has passed the first step, right? So f of 2 exists. The limit as x approaches 2 exists. However, that third condition, states that the limit as x approaches that value of the function should be equal to f evaluated at that value. So in other words, here, the limit as x approaches 2 of our function should equal f of 2. And here, you guys are all smart. I know everyone knows here that 2 is definitely not the same as 1. So is this continuous? No. And we can say fails to meet condition 3. Okay, so this was not continuous because it fails to meet condition 3. If you just look at the graph, of course, can we draw this without picking up our pencil? And the answer is no, right? We'd get to here, we'd lift up, fill in this point, come back over here, and continue. So, no, this is not a continuous function. Hopefully that makes sense. If not, let's continue to do more examples until it does. Okay, so let's look at the second example on this page. Okay, so here we have another graph we're going to talk about, is it continuous, is it not? Hopefully by now you can look at it and say this is certainly not continuous, right? Just by going off of the pencil method. So we try and draw, we pick up our pencil, and then we try and draw again. So no, this is not continuous, but let's talk about why it's not continuous. Here is another good opportunity to pause the video, try and work this one on your own, and then see if we get the same answer. So f of 1. So when x is equal to 1, we go off of the filled in circle here, and this one is much easier to see on the document camera than the previous. So thanks for bearing with me through the first one. So when x is 1, here we have a filled in circle that y is equal to -2. So f of 1, that point does exist. The y value is -2. Next, we're going to look at the limit as x approaches 1 coming from the right-hand side. Right, so the limit as x approaches 1 coming from the right, we start over here, we just trace along the line, and we arrive here at -2. Okay, so the limit as x approaches 1 coming from the right is also -2. So far, so good. It looks like maybe just based off of these two, maybe there is potential for it to be continuous, but we know better. So now let's continue. The limit as x approaches 1 from the left-hand side, start over here, we trace along, and we're arriving at this value of 4. Okay, so the limit as x approaches 1 from the left side is a +4. Right, and so the limit as x approaches 1 from the right is -2, which is not the same as the limit as x approaches 1 from the left, which is 4. So for the two-sided limit, we can say this does not exist. Okay, so the two-sided limit does not exist. So is this continuous at x equals 1? No, it is not. Okay, and this did not meet condition 2. Okay, so failed to meet condition 2. Okay, so condition 2 states that that limit must exist. All right, let's move on to our final example of this section. So here, f of -3. Okay, so I just want to point out here, looks like we have a vertical asymptote here. So a vertical asymptote at x equals -3. So f of -3, what do we get? Well, we get nothing, right? We have a vertical asymptote here, so it is undefined. It is undefined at -3. So really, if we were only asked to find is this continuous and not have to fill in the intermediate steps, then we could stop right there and say, no, this is automatically not continuous, and this one failed to meet our very first condition, okay? So if that's all that we were tasked with doing, find whether this is continuous or not, we could just stop right there. It failed the first condition. There's no point of going any further through the problem. But since here we're asked to find these limits and we just learn limits, I think it is still really good practice. So let's go ahead and do that. So here we're talking about the limit as x approaches 3 coming from the right side, okay? So here, and excuse me, I misspoke. This is limit as x approaches -3, not +3. So the limit as x approaches -3 of our function, but from the right side. So we trace. We get really close to that asymptote, and it just keeps going up and up and up and up. We talked about last class, that tells us that the limit is +infinity. Let's look at the other side of the asymptote. So the limit as x approaches -3 coming from the left side. So we start over here. We get closer and closer to -3, and we immediately drop down, and we keep going and we keep going. So this limit is -infinity. And so here, what can we say about the two-sided limit? Well, one side's going up, one side's going down. So here, this limit does not exist. All right. Hopefully that makes sense to you guys. That is all for section 1.2. Practice these on your own. Go ahead and jump and maybe do a couple homework problems as extra practice. Just get as much exposure to this as you can. It is a big concept. We're going to continue to use this for the rest of the year. Very quickly, I'm going to introduce section 1.3. We're not going to finish it out, but section 1.3 goes off of average rate of change. So here, section 1.3, page 12 in the notes. This is a concept that really you have already learned and may not even realize it, okay? So before even putting on your calculus thinking cap, think about other classes, other problems that you've solved before. So this says, if a car travels 110 miles in 2 hours, its average rate of change is blank. So what would that be? And if you're thinking 55 miles an hour, you are exactly right, okay? So 55 miles per hour. How do we do that? Really, we just took the distance traveled over the time. And so on average, if we traveled 110 miles in 2 hours, then on average, we were traveling 55 miles per hour. So that is our average rate of change, so the average rate that we're going over that 2 hour period. But now let's say, suppose you accelerate on the highway and you're glancing at the speedometer and you see that at that particular instant, we call this the instantaneous rate of change. So instantaneous rate of change is 55 miles per hour. So even though in this premise of a problem, we have the two of the same numbers, so 55 miles per hour as our average rate, 55 miles per hour at our instantaneous rate. These are very different things, okay? So average rate of change is going to be something that we are familiar with. We've done these before. Instantaneous rate of change involves ideas of limits and uses calculus, okay? So this is our next big thing. I'm going to stop today right here so that we can continue with this in the next class. But look forward to using limits to apply, to me, one of the coolest things from calculus. So you guys stay warm out there. I look forward to seeing you when we return to campus. Have a good one.